Large language models know a lot, they can do a lot, and you can build many applications with them. But sometimes you need things where LLMs can do their limits. You want to use private knowledge, you want to update this private knowledge now and then, and you want to sometimes have very large knowledge bases as part of your processes and of your templates. That's why we are looking into Retrieval Augmented Generation, one of the approaches on how to achieve exactly that. So before we get now too deep into Retrieval Augmented Generation, let's first talk a little bit about why we need it. So go to the open ChatGPT version and ask ChatGPT what your company had as a turnover, revenue, something last year in EMEA. It will give you either an answer where it says, I don't have access to your financial data, but if you can provide me with some key figures, like revenue streams or specific sales numbers for EMEA, I can help you analyze the work. Or it will, in the worst case, make something up. That's because we have to look a little bit deeper into where LLMs get their knowledge from. Actually, large language models like GPT-4o, GPT-3, all of these old ones are mathematical models that do not know anything, but they predict an outcome, so an answer to a prompt that you give in based on the inserted information and the trained structures from a training data set that it had. So you basically given a prompt and the large language model guesses according to statistics, what word comes next, what sentence comes next, what paragraph comes next. So in an iterative way, build you your thing first. So that means that there's not a single source of that answer that you get to a prompt, but it's more of a statistical mix-max that you get together that often sounds very good and often is very accurate, but you cannot trace an answer back to a single source. That's not how these statistical models work. Many people don't understand that, but that's a key, very key information that you need to know when you want to build these type of applications. I said in most of the cases, what you get out in the end actually sounds pretty reasonable and doesn't sound too bad. Where does that knowledge and where does that good guesswork come from? OpenAI has not published where or what data set they're using for training for a long time, but we know from a very old paper from GPT 3.0 and 3.5 that they have been using billions of tokens. So token has a correlation to a word from public internet calls, from forums, from blog articles, from books, over 60 billion tokens that were used from books and from the English-speaking Wikipedia. So that means that data set that was used to train this large language model, it's basically a representative of the common knowledge of the Western world. So I say very specifically Western world because it's an American company that mostly is covered through English-speaking sources. And of course, all of the bias that these sources may or may not have is ingested into this model. So I hear sometimes when GPT 4.0 came out and there were some really strange answers coming out and people said, ooh, that model produced hate speech. Ooh, is this now an evil model? No, it's not an evil model. It's just learned the underlying structure of how language works with that knowledge that it was trained on. So if you have something that triggered something hate speech, that means that in your training data set, there might be a combination of different sources that would have led to that. These models are very hard and very expensive to train. So that's why models like GPT-4 and 4o and all of the new ones that are coming, if you want to update them with certain knowledge that was not there when you trained them, you need to retrain the model if that information gets updated, which is a key drawback from this approach. So when we are talking now about only pure LLM-based applications with no other supporting structures, I call that now, around them, we have the following 5 major issues. They're static. This was what we talked last about. They only have been trained on a dataset available to a certain time frame. So they are frozen in time. You cannot just update an LLM because this is pretty costly. You basically have to retrain the LLM if there's no knowledge, or do a fine-tuning, even though getting old information that is outdated out is very hard. These general purpose large language models often lack domain-specific knowledge or company knowledge. Of course, we have seen that the OpenAI models have been trained on the publicly available general knowledge from the internet. And of course, that's not your company's internal knowledge. It's not your revenue statements. It's not your internal old project reports that you might want to search for a new project. And it's also not something that you can just swing from A to B. And that is one of the biggest drawbacks. LLMs are for us black boxes. It's a very complex and very deep neural network, and we cannot trace back which exact source has led to an answer, because it's just a statistical combination of structures that we have learned from all of the sources. So there's not a single source for an answer that you get, but it's many. And especially when we're talking about enterprises, where you have critical tasks where you need to verify something before you sign off, and where you don't have any tolerance with hallucinations, this becomes really problematic. Hallucinations is the other term that we have for that, is if a large language model just makes something up that is actually not true. It's not because the model is thinking, did I have that in my private data or not? No, it's just because in the same way statistical models works. You also prompting a model telling him, hey, please don't hallucinate, will not help it, because the model itself is not aware of what it does right now is an hallucination. Basically, everything what a large language model does is a hallucination, but in many cases for a good model, this hallucination is the truth. Yeah, that's an important concept when we need to think about the limits of that this approach has. And especially for companies with verifiability for critical tasks, this cannot be underestimated. LLMs are hard and costly to create. There's only few organizations that have the financial and human resources to produce and deploy foundation models, or yet even to fine-tune LLMs. Fine-tuning is a term for basically using a foundational model and adding an additional training set on top of that to basically retrain and fine-tune this model. A lot of people think fine-tuning is always the way to go. No, because in the end, when you have fine-tuning, in the end, you still have a large language model that has all of these drawbacks here, just with a bigger data set. So that's why I'm not a big advocate of fine-tuning, apart from situations where you have specific vocabulary. Specifically, I would say generalized industry knowledge. So there's a bunch of people that train specific models for the production industry, for physics, or for financial modeling. Then this type of fine-tuned model makes sense. But not if you want just to have a specific type of information in there, then fine-tuning is not the way to go. And large language models, they have context size limits. So what you put in a prompt has a limit. The GPT-4o model can take, for example, 128,000 tokens. That might be a book with 100 pages, yeah, which helps you quite a bit. But at some point, you might want to have bigger knowledge bases where you get information from than just a 100-page book. And also, the bigger the context it gets, the harder time the model has finding the right and relevant information to your specific prompt. That's what we call the needle in the haystack problem. So if you give it a lot of context, it's very hard. And there's one specific information in one sentence in a 100-page document. Large language models sometimes have real challenges of figuring exactly that out. And that's why these problems are especially impactful for enterprise and for company applications with large language models for Gen AI-enabled applications. And one of the solutions and the go-to solution is basically augmenting LLM generations with data retrieval. And this combination leads to the term Retrieval Augmented Generation. How Retrieval Augmented Generation, or we will just call it RAG, basically works is we have two phases. In the first phase, we are building up a vector database with all of our knowledge. So we are building a knowledge base. That works in a connection of different things, raw documents, chunking vectors, and putting that into the database. We will look into that in more detail in a second. And then whenever we have a completion, so when you would like to query and you would like to have an answer, then we do semantic search on that generated or on that created vector database, and to create an answer that is augmented with the very specific data that we have found in that database. We will look deeper into the individual steps now. So the first thing that we have to do when we are creating retrieval augmented generation pipelines is called chunking. Chunking is nothing than you start with your whole knowledge base. That might be dozens of documents, Word documents, PDFs, whatever it is, where you have different pieces of text inside. And chunking just means we are putting these large documents in smaller chunks. These smaller chunks will later be in vectors represented in our vector database. We'll talk about that in a second. The important thing about the chunking is basically chunks are small excerpts from the real text that in itself have in isolation meaning. And we will later search in the isolated meaning of these chunks for the things that are most similar to what we are looking for. There's different chunking strategies. You can take text and you can do fixed length chunking. You can do semantic chunking, or you can redo recursive chunking or other specialized chunking techniques. Let me give you a little example on how that looks like. You think about this here as a white paper that I recently wrote. So this has quite a lot of pages. We are looking to create a knowledge base out of this very specific document. So when we are chunking, we are basically cutting this text into different sections that we call chunks, and translate them into vectors, which is the next step that we are going to talk about. Translating a chunk to vector works with an embedding model. Embedding models have been actually around for quite some time, but an embedding is basically a numeric representation of the semantics of a piece of text. Sounds now very bulky, but it will get clear. So what we are doing in this part, we are taking each of these chunks individually. We are creating an embedding that produces a vector for that chunk that represents basically the semantics of that chunk in one numeric representation. We do that for all of our chunks, and we put them into a database. And this database is a vector data. Here on the right side, you see a two-dimensional plane where we see different pieces of text. Imagine we would do very small chunks of only one sentence, and we would create embeddings from them. Then these embeddings, they have a certain representation and they have a certain closeness to each other that we can represent. Now think about that here. We have here one sentence, a little boy is walking. We have not too far away in this coordinate system, a little boy is running, because a, little, and boy, semantically similar to that sentence, and walking and running are not too far away from each other. On the other side, we have a sad boy is walking. Again, a boy is walking. Who's the one who's walking? It's here a little boy, and here it's a sad boy. So this is semantically also close to this sentence. This here is a little bit farther away from this sentence, but still close. Then we have here a man is walking in the field. So we have here someone who is walking, but this time it's not a boy, but it's a man. But the concept of a boy and a man semantically are very similar to each other, or very related to each other in that way. And then we have here a dog is walking past a field. We have also somebody who is walking somewhere and past a field. So this here is semantically very close to a man is walking in the field, but it's semantically a little bit farther away from a little boy is walking. And in that way, an embedding model will basically represent these semantically closeness in an encoding that symbolizes basically the semantics of this search. It's quite hard to grasp and it's quite hard to understand, because it's also not that easy that this is just a two-dimensional coordinate system. It's more of an n-dimensional coordinate system, but it's much more than we as humans can comprehend. And that's why all of these models are so powerful and very hard for us to understand. But the key point here is embedding helps us to deal with the semantics of the sentence or of a whole paragraph, of a whole chunk, however big it is. And by this encoding, by this embedding, we can do semantic search. We can find text that is close in terms of semantics. And that's one of the real important things that we have now with this type of embedding models that we do not have for keyword search. Keyword search, works completely differently, right? You're looking for the term boy, you will never find the term man, because keyword search, the boy and man, they don't have any characters in common, right? It's N-A-N and B-Y-O. There's no character in common. So a keyword search wouldn't understand that a boy and a man are semantically close to each other, but an embedding does. And that's the key thing to understand here. It's an abstraction, but think of it as a mindset. And we use this principle now every time, not in the preparation phase, but every time when we have a certain query to that knowledge base. So every time we would like to search our knowledge base, we are doing a semantic search and we are looking for our query. So if you're saying, okay, I am looking for a boy who is doing something, that's your query, then we are creating an embedding of that query. And we check through all of the embeddings that we have stored in our database, and we find the vectors that are closest to it. Not only the top one that is closest, but a top 2, 3, 4, 10, the top K that is closest to it. And that means we will find the text chunks that are content-wise the most relevant to the text that we inserted. This search does not need an LLM. It doesn't use the whole big expensive model. It uses an embedding model basically to translate our query and calculate similarity. So to translate our query as a basis for later similarity calculation. And it uses a similarity metric, for example, the cosine similarity, which is very cheap to compute and very fast to compute to evaluate. So that means we get speed and we get cheapness by using embedding models and similarity calculation instead of using a large language model. It's much faster, less costly, and without the limits that we have with an LLM in the context. So for big amounts of data at a reasonable price, no needle in the haystack problem, clear traceability of the source, embeddings and retrieval augmented generation with vector databases is the way to go. There's much more that you can do. You can do metadata filtering so that you have basically different layers or different subsections of your data sets that you pre-calculate, because depending on how big your database gets, there might be different chunks that are semantically very close to each other in terms of the representation, but sometimes it will not help you. So there is a lot of, let's say, parameters that you can tweak in this process. What we do then is basically we select the 10 top or the K top vectors that are semantically closest to what we are looking for. And then we get the full text chunks again from our data store. And then there is an optional step in retrieval augmented generation, what we call a retrieval re-ranker structure. You don't need necessarily to do that, but you can do that. Optionally, we take the top K results and feed only the top K results into a large language model, because large language models are even better at what you would call understanding, basically to do correlations than in an embedding model. But on the other way, an embedding model is really factor 10 to the power of 2 cheaper and doesn't come with the limitation. So we are doing a little bit of a trade-off between price, efficiency, and quality. And if we are saying, okay, we do this top K results, instead of giving all of the database that we have, we are only giving the top 10 results that we did identify with a pretty cheap but still pretty powerful approach. And we're giving that now to the good quality and highly precise LLM to re-rank them and get an additional quality improvement. And in that way, we have then basically pre-selected the context that we give, and then we put this pre-selected context into the actual large language model completion for end-to-end retrieval and completion. This means that retrieval augmented generation solves a lot of issues. With RAG pipelines and LLMs, your knowledge bases are not static anymore. We can relatively easily add information, delete chunks, or update it whenever it's there. That's a problem that you would have if you only would rely to an LLM. You can insert any type of domain-specific and private knowledge. These vector stores that you build, they are just normal databases like your SQL databases that you have in your company already. So you can make them private, and they don't have to be available to everybody or everybody who wants to have the model. So it's available for everybody who has access to the database. So you basically have the model layer and the data layer, and you can clearly distinguish between them. And it also has the beauty that we can really track and trace back the output to its source. So we can look into chunks, then go into the embeddings and look into the full text. That's all possible. You can't do that by just using a large language model or even a fine-tuned model. And compared to only LLM-based approaches, they are pretty cheap and not a lot of technical overhead is needed for. And in that way, we can really deal with large amounts of data and have more advanced filtering. So pre-selection, retrieval, re-ranking for data, then feeding it into your LLM with the prompt of the output that you would like to have, and then getting your answer. And that's why for most of the cases, this is the go-to mechanism for enterprise generative AI applications. When you have private data, when you have large knowledge bases where you would like to do something that is very specific to your processes with verification end-to-end, where you can trace where this information is coming from and where to go through.